Hello everyone, welcome to this presentation. I am Bertrand Teguiel Tabudia and I will be presenting this joint work with Wolfram Kuff on the representation of non-holonomic power series. It is always a pleasure to participate at the Maple conference, and we thank the organizer for this opportunity to present these results. Now, let us start. Here are some references of this presentation. The two first are books on computer algebra, where we take some identities involving non-holonomic expressions. And also in the first book, there is a definition of what is a normal form. We will use this to represent our power series. And the third reference is a well-known paper on holonomic functions. There you find some proofs about the non-holonomicity of the Bernoulli numbers or the tangent function. And the fourth one is my PhD thesis, where the idea of this presentation and its accompanying paper was first developed. As outlined after an introduction where we state the problem and how we intend to resolve it, we move on to the second section where we defined the class of delta 2 finite functions, a subclass of the family of non-holonomic functions, which is rather large. We want to consider those functions that can be processed through algorithm and we cover most of the non-holonomic functions that we use to manipulate. In the third section, you describe the first step and the main step of our algorithm, computation of quadratic differential equations. And from this step, we deduce the power series representation after a conversion into a recurrence equations and write the power series in a recursive form, which is also a normal form. Now, let us introduce. What do computer algebra systems give as power series for tangent, secant, cosecant, hyperbolic secant, and all these non-holonomic functions? Generally, it's either a pattern matching models or the input will be returned as output. So we investigate this question and propose an algorithm with implementations in Maple and Maxima. Let us see what is currently done in these two computer algebra systems. If we take, for example, Maple, here are the input. If you want to find the power series formula of a given expression, in Maple, we think about of using the FormalPowerSeries package, which find the power series formula. For this, for example, if you try to compute the power series for all these inputs, you see that the input is returned as output. In Maxima, the result is different. If you evaluate all these cells, you see that the power series formulas known from the mathematical dictionaries are returned. Here we see the Euler and Bernoulli number appearing. However, since this is a pattern matching model, so there is no deductive algorithmic process behind the computation, the mathematical deductive approach. This is why one will expect, although one will expect the generating function of the Bernoulli numbers to be computed by the algorithm, in this case, this is not possible. So, and we want to present here a method that will compute the power series formulas for all these such type of functions. We have seen Bernoulli and Euler numbers appearing in these power series representations. And here are the basic definition of the recurrence of these numbers, the well-known recurrence relations of these well-known numbers. No, so we see that the problem here is the non-holonomic character of the power series defined by the Bernoulli and the Euler numbers. And our first observation is that the usual derivative operator can be sometimes, while differentiating, generate some square or product of derivatives in the process of differentiating. As you can see, for example, with the case of tangent, where we have 1 plus tangent square. So our idea is then to extend the computations which are done for holonomic functions for another class of functions. For example, if with our maple implementation of our algorithm, we can find the power series formula for the reciprocal of log of 1 plus z here given in formula 6. As you can see, this is a Lorentz series, so our method is also able to compute a representation in here in a recursive form for the coefficient of many non-holonomic power series. Basically, here is how our method works. Given a function, the type of function we consider will be made precise in the next section. We find the quadratic differential equations, which can be holonomic, satisfied by that expression. We convert that quadratic differential equation into a quadratic recurrence equation for the power series coefficients. We say quadratic recurrence equation because they are also product of index variable in the recurrence equation found. And at the end, we write the power series in a recursive form with enough initial values. This process defines a normal functions that allows us to either to prove identities between non-holonomic expressions, as for example, this equation 7. Now, let us move to the second section and define what we call delta 2 finite functions. We made some assumptions. The derivative of order -1 is 1, the derivative of order 0 of f is f, and we will be considering a field of characteristics 0 for the coefficients, and generally this is the field of rational functions. We consider differential equations with polynomial coefficients. So here, in this case, if we define the quadratic differential equations, that is a differential equations where the coefficients of terms where they are product of derivatives are not all 0, so that at least one product of derivatives appear in the differential equations. In this case, the differential equation is said to be quadratic. But we would like to consider a differential equation that will also be holonomic. And here is how we want to define our class of functions. Like for d-finite functions, we define delta 2 finite functions to naturally extend the class of holonomic functions. Holonomic functions are also known as d-finite functions. And then we introduce a derivative operator delta 2z, where the 2 here means product of derivatives, including the square. And here is the ordering of the differentiation. So the integers in parentheses here represent the order of the derivative, and the result is what you see as product of derivatives for any integers appearing in the parentheses. This can be seen as an infinite lower triangular matrix, and we can establish a one-to-one map between the integers in parentheses and every cell of this matrix. This is how we found the formula to compute the derivative of order k for the delta 2 operator. Then we find this formula here to define the derivative of order k of a given expression f. There is the product where ij are computed in this way. So this allows us to define the class of delta 2 finite functions. A function f is called delta 2 finite if there exist polynomials p0 up to pd, not all zeros, such that these differential equations is satisfied by f. Note that this differential equation can be holonomic, since the delta 2 operator also compute the usual derivatives. Note that this differential equation we also call it delta 2 finite equations, since we talk about the delta 2 operator, or quadratic differential equations. And most of the differential equations we compute are quadratic. So how do we compute quadratic differential equations? Our idea is to use the method of ansatz with undetermined coefficients by replacing the usual derivative operator by delta 2z that we just defined. The algorithm iterates on the order of the differential equation, For each positive integer n, we seek for rational functions cn minus 1 up to c0 over the considered field so that this handset is satisfied by the given expression. If this is successful, we clear the denominators and reduce the delta to finite equation soon. Otherwise, the value of n is incremented and the process continues until a certain upper bound given by the user or fixed with a default value in the algorithm. Let's see, for example, for the reciprocal of log of 1 plus z. For n equal 1, we seek for c0 such that this ansatz here is satisfied by the reciprocal of log of 1 plus z. However, the third derivative over f of z is not rational, so we move to the next step. And in the second step, we seek for c0 and c1 such that this ansatz is 0. This is equivalent to this expression here, and having this equal to 0 is the same as having the numerator equals to 0. And solving this equation for over the ring of polynomials in the variable log of 1 plus z gives us the solution c0 and c1 here. And plugging in these coefficients give us the differential equations. And after clearing the denominators, we then have this differential equation with polynomial coefficients that we wanted to compute. Let's see, for example, the computation in Maple. Our algorithm can be downloaded in this web page here. And we consider, for example, for tangent, if we compute a differential equation, then we have this one, which is holonomic and quadratic. We can check that tangent is solution by solving the differential equation with the maple dissolve command. Here is for secant of z, we have this differential equation, which is also quadratic, and we can check that secant is also solution. We consider a more difficult example, tangent of z power k. This takes a little time, and then we have this differential equation. For this one, the dissolve command will not give an explicit solution. However, we can still check that tangent z power k is solution by plugging in the input and simplify and get 0. Now, let us move to the next step, write normal forms of the delta to finite power series. We assume that the power series of f is given by this expression here. Note that the Lorentz series case can always be reduced to this particular case. We also recall the definition of the Puchhammer symbols given here, which will be used to write the rewrite group to define the rewrite rule to go from the differential equation to the recurrence equation. When expanding the left-hand side of the quadratic differential equation obtained, one finds two types of differential monomials, the definite case and, let's say, the delta to finite case. The definite case is known, the rewrite rule is given by this formula here in 22. For the delta to finite case, if you consider the derivative of order I, then we have this formula. Then if you take the product, by applying the Cauchy product formulas, then this is what you obtain. After multiplying them by z power p, you shift the symbol n and you get the rewrite hold in formula 25. So this is how we compute, we convert the differential equation to the recurrence equation. Let's see, for example, computations with Maxima. Our codes can also be downloaded in the same web page. We have Maple and Maxima version of our implementation. If you find the recurrence equation for tangent, here is what we got, and you see you can't avoid the summation here. This means that there is a product of derivatives. Sometimes Maxima does not display the summation symbol. This is for the generating function of the Bernoulli numbers. This is for log of 1 plus sine z. So you can, as you can see, we can compute recurrence equation for all these expressions. Now, for normal forms of delta to finite power series, the last step of our computation consists of using the obtained quadratic recurrence equation to write the highest order index variable in terms of the orders. And with necessary initial values, this defines a normal form for the power series considered. And then we have Exability's theorem, which says, given a delta to finite function, the following steps define a normal form of the power series representation of f. The first step is to compute a delta to finite equation satisfied by f, then expand the left-hand side of the obtained differential equation and convert it into a recurrence equation using the rewrite rules, the two rewrite rules that we have given, and use the obtained recurrence equation to write the highest order index variable in terms of the preceding ones with the required initial values. The number of necessary initial values is determined from the recurrence equation and the differential equation. For example, for the generating function of the Bernoulli numbers, here is the recursive formula of the coefficients. And from this formula, we can recover a well-known convolution identities involving the Bernoulli numbers. For example, starting from the fact that the coefficients have this relation with the Bernoulli numbers, and using a basic fact about the Bernoulli numbers, which is the only odd term of the Bernoulli numbers is the term with index 1, then we deduce these formulas, which is well known and can be found in many references about Bernoulli numbers. This shows somehow that our algorithm can be used to recover, or even, who knows, find some identities involving Bernoulli or Euler numbers. Now, let us see some computations in Maple and Maxima. We use our implementation to also compute truncated series of any order. Here is, for example, we compute the truncated series for second, and using our implementation Q-Taylor. This is not implemented in our Maple package because it's not efficient as the built-in command. However, in the holonomic case, this is more efficient. So we compute the Laurent polynomial or the Taylor polynomial, and as you can see, they are identical. For tangent of z, we have this one, and using our Q-Taylor, we also have the same truncated series. Now let's see some series computation. For tangent, the found representation is here, this with 3 initial values. For the reciprocal of 1 plus sine z, here is what we got with 2 initial values. We can also prove identities if we consider, for example, these two functions, f and g. Then the representation for f is the same as the representation for g, which shows that f and g are the same in this neighborhood of the power series computation around about 0. And you just have to substitute either f by g or g by f in the representation and see that all these, the two representations coincide. Moreover, our algorithm can prove that this is the difference is 0, since all the necessary initial values are 0. So this is all for our presentation. We thank you for your kind attention. Our implementation will be available in the FormalPowerSeries package. So starting from the 2022 release of Maple, we thank Jürgen Gerhard for helping us to implement our algorithms in Maple and make this available for researcher and the public. So thank you very much for your kind attention. The computation of differential equations will also be available from the Fine OD package, so anyone could use it in the future. Thank you for your kind attention.